I didn't miss anybody's valuable. Uh-oh. So we're figuring out the sound. Well, I hear something. See, Natalie's the one, our
guinea pig.
Guinea pig.
I'll just voice over right now.
Yeah, that's awesome.
On film, and it's being filmed the whole thing.
Yeah.
Oh, actually, it did start. Yeah, it did. We'll add the audio later.
Oh, what was the end a little bit?
Was that? It felt like it was organic to the room. Oh, are you switching to this one and not the rooms? Horrible. Okay, so we're just going to use the small speakers? Huh? For this one? Okay. We'll want to get going then. Okay. Well, Natalie, it's your show. Go right ahead.
Okay. I guess just play the video.
Hi, I'm Natalie, and I'm an engineering student at The Ohio State University. And I'm here to tell you about the laser measuring device 4H Engineering Challenge. In my lab, we do research with DNA origami, which is building tiny nanoscale structures out of strands of DNA. We've built things like boxes, spring scales, and gears, and some days that we use in cancer research. But they're so small we can't even see them with our own eyes. I have my three structures separated into these boxes, and they're mixed in a solution with water. But I forgot to label them, and now I can't tell them apart. What I do know is that each of the three DNA origami structures have a different length. So if there's a way that I can measure the structures in each of these mystery boxes, I'll be able to tell them apart. But how do I measure such a small structure? The answer is laser. Your DNA origami structure is printed out and attached to a cardboard easel made out of a cereal box. Your goal is to measure the distance from one end of the structure to the other while standing 3 feet away by using the laser pointer and 2 small mirrors. In real DNA origami, we attach fluorescent particles to each end of the structure, and when they're hit with the light, they glow. But for our challenge, we'll be using mirrors instead of fluorescent particles. It's very important to position your mirrors at exact 45-degree angles to ensure that the light is reflected properly. The next stage is to build a launch device to hold the laser and a catching device to stop the reflected light. My device doesn't work that well, so I need to go back and make some new drawings to improve my first design. Once the light is reflected back, you can measure the distance from the laser pointer to the reflected light to successfully identify the DNA origami structure. When your device works well from 3 feet away, try 10 feet away, or the other side of the room. Does it still work well, or are there more improvements that need to be made? Good luck, engineers. I know you can do it.
Alright, that is super awkward from all of you. But, so that was the project. It's been refined a little bit. And this is my test setup, I guess. Basically exactly what I showed in the video. So quickly going through the paper, you see on page 1, no, I'm kidding. Basically I kind of set up this fake scenario that I didn't label my tubes and I mixed up my pieces so it's their job. Yeah, I do.
Just so, no, just the two in the bathroom. Thank you. Thank you.
So I'm having them kind of try to solve this problem to measure them, but without using like a ruler or traditional method that they're used to measuring objects with. So one of the key things is basically getting these mirrors to line up correctly, and that was one of the problems that we had in class. I had set them up, but they weren't exactly 45 degrees, and then with travel, I think I kind of messed up the devices a little bit, so they had a really tough time with it. So I thought it'd be cooler anyways for them to actually build this part. And so I really kind of try to emphasize how that's one of the most like critical parts to the design challenge. Going beyond, that was kind of, that was like the original design challenge was trying to measure several, like when we did it in class, was trying to measure several different structures. And then I've also added things like measuring it from 3 feet away, then 10 feet, then further away. Also changing the angle that the mirrors are lined up so that they reflect like with larger angles, and they do like a little bit of geometry to try to solve for it. And I included a little easy diagram of what the goal is that they're trying to do, and then these printouts so that they have something to base these designs off of, although they could really be just about anything. So, yeah. And then, so I guess like the kind of like reflection portion of this, I kind of went into this all business. I'm a woman in engineering, and I wanted to spread my knowledge about what engineering is, and my dad's an engineer, so I wanted to, I was given an opportunity that a lot of other people aren't. I kind of grew up knowing what engineering was. There's a wood shop in my basement, so I'm kind of used to being around power tools and soldering things. So I went into this all business, like I said, and we had 8th graders, so I was like, oh my gosh, these guys are going to have such an attitude, and they're not going to be interested at all. And really kind of just the opposite happened. They really kind of ended up liking us, and I ended up liking them, and really kind of became more invested in just kind of being dorky for an hour and entertaining them, putting a smile on their face. And if I don't know what their home life is like, I don't know what their family situations are like, but if I can make an hour and a half of after school kind of fun for them, then I think that's okay too. If they learn something about engineering on top of it, like that's the bonus. So that was kind of my little reflection from it. So that's what I got.
Alright, Nate, you're next. Yours on the YouTube channel.
Yeah. Do the gravity car one.
Okay. That's just here it is.
No, it really is not. They're similar enough that I can make them material.
That's so big.
I'll bring it up there.
We need like 2 more over here, Molly. 3 more over here.
It's like 2 more down here.
I'll grab one of these. One thing down there.
I did not.
I would not.
Let's do one of these for
Your voice is enough.
Yeah, but not too much actually.
Stop at the gas station, which saves a lot of money and makes owning a car
Oh,
more
that's my voice.
That sounds good.
reason to have a fuel efficient car.
Come on.
Okay. Well, this is going to be yet another makeshift.
Ramp? Seriously? Oh my goodness. Every
This one-
single time.
Well, no, I've actually used this one several times now just because of stuff at my house. But it's the first time you guys have seen it.
An official ramp.
It just shows how versatile this sign challenge is. So this isn't the ideal length, but given the circumstances, we're just going to go with it.
Alright, would you like to start with the video as well?
Yeah.
Okay. Are you ready to go?
Yep.
Okay, go right ahead.
Hi, my name is Nate, and today we are going to be learning a little about cars. Many of us have ridden in cars before. I bet most of you got here today because of some sort of car or bus. Cars are a very normal and important part of our society. Have you ever thought about how they run? Most cars run on gasoline, which is a type of fuel. The engines burn the fuel to propel the cars forward. How well an engine uses the gasoline is called fuel economy. Fuel economy is measured in something called mpg, or miles per gallon. Basically, it's how far you can go with each gallon of gas. If a car has a high fuel economy, it's fuel efficient. There are many great reasons to make a car with a good fuel economy, but the biggest for most people is money. Gasoline is needed by hundreds of millions of people every day, and unfortunately, there's only a limited supply, which makes it expensive to fill every tank. A better fuel economy means fewer stops at the gas station, which saves a lot of money and makes owning a car more affordable. Another big reason to have a fuel-efficient car is the environment. When an engine is finished with gasoline, it spits it back out into the air as pollution, which is bad for the environment. A better fuel economy uses less gasoline, which means less pollution is produced. How do you make a car fuel efficient? There's a lot that goes into designing a car, but weight and wind resistance are two major factors that are easy to think about. If a car weighs a lot, then the engine has to work harder to move it forward. The same goes for wind resistance. Don't believe me? Have you ever stuck your hand out the window while you're in a car? If you have your palm facing forward, your hand gets blown back because you are catching more wind. But if it's sideways, you can go through the wind. That pushing back gives wind resistance, and it can make it harder for an engine to move a car forward. In an effort to ensure that car companies are making fuel-efficient vehicles, the US government passed some laws called the CAFE standards, which make sure that new cars meet a certain minimum mpg. Right now, the average new car gets 27.5 mpg. By 2016, cars need to get 37.8 mpg, and by 2025, they need to get a whopping 54.5 miles per gallon. It's up to engineers like us to make that happen. In order to get you ready for this challenge, we are going to design our very own gravity cars. Instead of gasoline, our fuel is going to be gravity. We will build our cars out of these everyday materials and launch them down the ramp. Sounds simple enough, right? Almost. Not only do you need to design your car to roll down the ramp in a straight line, there will also be a fan at the end of the track blowing back at you. Start by building a simple prototype. Once you have that ready, test it out and brainstorm how you can improve it. Your challenge is to design a car that will travel the farthest without hitting the fan. If it hits the fan, try again. If it falls off the track, try again. Remember, we only have a limited supply of resources, so really think about your design before you build it. Make sure you draw out your design and list the materials you'll be using. Once you have your design ready, your instructor will give you your requested materials so you can get started.
I do that too. I wish. Okay, so I'm not going to put the fan on because that's going to blow everything around. But the video showed how rolling the car down the ramp, trying to get as close to the fan without touching it. If you want to go through the packet, pretty similar to what Natalie was talking about, following the template. Couldn't really come up with a really good situation statement, so I just talked about someone getting fired because of not being able to afford a car and having to rely on public transportation. Yeah, and then just going through it, some more pretty pictures, just so you know how to keep the design going. And then, yeah, the second challenge that I have, pretty similar, focuses again on fuel economy, except this time it's an aluminum foil racer. So I only have one track set up right now, but the idea is to have several, and for each student to make a car that's powered by a DC motor, and that when you put it on, shoots forward more. With a less smooth surface, it goes farther.
Oh, shout. Sorry, it was funny.
Yeah, and then I think the biggest takeaway for me, again, coming in, not really sure what this class was all about. I just kind of, it was an opportunity to do research over the summer, and that was my initial motivation. And I thought it'd be fun to work with kids again in an engineering standpoint. I was a camp counselor for a couple of years over the summer during high school, and I loved working with kids, so I thought engineering and kids, that might be fun too. I never expected to have the experience I had. Just the impact that I saw that we had on the kids. Like being a camp counselor, I wasn't surprised that we had a huge impact on kids, and like it was a lot of fun. They really got to like us. But being their instructor and having a similar impact, one of our kids, Brandon, was very upset when it was our last day, and it was just really amazing to have that impact on someone, and engineering being the reason why that impact was happening. And then, so that's an awesome impact, but also just with the future, I don't know how many of you had interviews and stuff like that throughout this semester, but employers love TEK8. Like, as soon as I step into the interview, they want to talk about TEK8, because it's something new, it's something that's really actually making an impact on the community. And I have a co-op next semester with Honda, and like that was a huge reason why it set me apart from everyone else. So make sure you guys talk that up. Yeah, that was my experience.
Okay, who would like to go next? Big Jack. Who is the me? You'll be next then.
Sir?
You want me to pass those out while you get
Nah, I got it, it's fine.
Thank you.
Yeah.
You can speak t-shirts.
Yeah.
You can't. You're kidding.
We're going every day over there. This is the last chance I had to wear the t-shirts. I figured.
Is that right? That's awesome. So that branding, right?
Oh yeah, long time. Like to catch some video.
Hi guys, my name's Jack. I'm.
Got one of these?
You know what? Yes.
Hi guys, my name's Jack. I'm a college.
I'm just gonna grab my test set up.
Go ahead.
Alright, ready to go. I'll start with the video as well.
Hi guys, my name's Jack. I'm a college student studying chemical engineering. And last summer I did some research in something called microencapsulation.
I think it
And
is.
that's what I thought originally too. But
It was working earlier.
Yeah,
just a second ago.
I love my facial expression. I should just change that up for the video. That's better.
hi guys, my name's Jack. I'm a college student studying chemical engineering. And last summer I did some research in something called microencapsulation. You might be thinking, what the heck is that? And that's what I thought originally too. But you probably already know what micro means. Micro is something that's really, really small. Like maybe, for instance, this marble. This marble's pretty small. But we're talking about something maybe 1,000 times smaller than this marble. Heck, maybe even 10,000 times smaller than this marble. We're talking about something so small that you can't even see it. So then what's the encapsulation part of microencapsulation? Encapsulation is putting something into something else. So if we wrap foil around this marble, then we could say it's encapsulated. You may have heard of someone getting cancer and having to go through something called chemotherapy. The chemotherapy heals their cancer, but it can still take a big toll on their body. It makes them feel sick and they might lose their hair. All said and done, there's a lot of bad side effects to chemotherapy. But with microencapsulation, we can alleviate a lot of those side effects. We can put an encapsulation around the super tiny cancer drugs and make them have less negative effects on the patient. So the person can still be healed of their cancer, but feel less bad during the process. The apparatus I made here is pretty simple. I'll explain what it's used for later, but for now I'm going to explain to you how I made it. It's just 2 cereal boxes taped together to make a long ramp. And then I put saran wrap over the ramp so it'll be waterproof. I used a Cheez-Its box to support it. These materials are the ones I chose, but really you can use any materials that make us a nice ramp that we can roll things down. So what's the apparatus used for? The apparatus is going to be used to roll down marbles like I showed you before. The difference is, before I showed you how I would microencapsulate a marble by putting tinfoil around it, but for this experiment, we're going to pretend that these marbles are already microencapsulations themselves. When you create microencapsulations, they're drenched in oil. But before the microencapsulations are useful, they have to have all of the oil drained off. So we need to make a device on top of our design apparatus that can totally separate the microencapsulations from the oil that they're drenched in. For this experiment, marbles will represent microencapsulations, and the oil will be represented by water. There are two parts to this design challenge. The first involves separating marbles and water so that water drains off the ramp and ends up in this bucket here, and marbles stay on top of the ramp, just like I showed. The second part of the challenge, which is a bit harder, is to separate marbles and water yet again, so that all the water again drains off, but marbles end up in a cup outside of the original design apparatus. I use my hand as an example, but you'll have to use the materials provided. If we can solve the problem of separating microencapsulations from the oil that they're drenched in, we can help cancer patients everywhere. Do you think you're up to this challenge?
Thank you. So that's my video. Then I've got my documentation out here. I kind of keep playing up that story about people having to suffer through chemotherapy, how bad that can be, how much of a struggle that is for so many people, and then the fact that microencapsulation can help so much with that. How it actually works is by putting a microencapsulation around a cancer drug, there's slightly more space between tumor cells than there is between normal cells. So with that larger encapsulation, the cancer drug will only fit between tumor cells and no longer fits between the normal cells, and that can therefore only kill the tumor cells off, which is really great. And that's what my research was on. Besides that, I just tried to follow the template as best I could. I outlined how to build the prototype, how to build this design apparatus. I would have a picture of the design apparatus, but I thought that was a little redundant since I kind of explained it in the video pretty well, I thought. What's important about this is just that the materials are kind of a fluid thing. You don't have to be rigid in saying that, okay, use 2 cereal boxes, use a Cheez-It box, use marbles. I mean, you really could use almost anything. You could make a ramp and then you could roll peas down it. You could separate out the peas, and that's what I think is nice about it. That, I mean, it's got a lot of ways it can go, and that makes it maybe easier to do. For the going beyond section, I think we should encourage students to use less and less material. We didn't get the chance in the amount of time we had during our design challenges to do that, but in a longer, more drawn-out setting, maybe people could encourage their students to use less and less materials, and make a design challenge that really works great using as little material as possible. As overall takeaways from this class, I mean, I think the biggest thing is presentation skills. I think at the beginning of the year I was kind of noticeably nervous to present in front of people, but now I'm really comfortable, honestly, and that's really great. That's makes it easier on me, and it makes me probably seem like a better presenter too, because I think I was shaking at the beginning of the year, but now I hope doing an okay job. So there's that, and then just the overall realization, I guess, that teaching is an option for me. I mean, I know I'm going to graduate and get my 4-year degree in engineering, that's for sure, but then after that, I mean, there's a lot of ways to go. I could go into industry, and then there's higher education, and maybe that higher education would be in education. I really don't know, but I know that now I can add that to my repertoire of possibilities that maybe I'll be a teacher someday, because I really did enjoy it, and it was a lot of fun. Felt like I had a great impact, so it was really exciting.
All right.
Okay, Michelle, go right ahead. Is that a SolidWorks model? Rolling? Yeah. I look forward to it. That'll be great.
You need one. So talk.
Thank you.
Sir. Might be 2.
Thank you so much.
Oh, that's nice of you.
It's a great presentation.
Thank you very much.
I'm Shane Piedmont, and I'm research graphene at The Ohio State University. Graphene is a two-dimensional structure of graphite or pencil lead. people are studying graphene to make electronics better because graphene is lightweight, conductive, flexible, and very strong.
Shayla, is that on the
And you can make
video?
really cool electronics at home with graphene. So, but before I show you how to do that, I have to teach you three things. I have to teach you closed circuits, current, and polarity. First, a closed circuit is a complete circuit. But you may be asking, what's a circuit? A circuit works very much like the organs in your body. The blood vessels and the veins carry blood through your body, much like wires carry electrons or current through your electronic devices. Thus, a complete circuit is when all connections are made such that your electronics work. This can be demonstrated with a flashlight. When a flashlight is in the off position, the circuit is incomplete and you get no light out of the flashlight. But when the flashlight is in the on position, the circuit becomes completed and your light turns on. The second thing you need to know is current. And current is the flow of electricity in a device. And current, as well as your power source, is what keeps devices working continuously. Third thing you need to know is polarity. Polarity is the direction through which current can flow through a device. Polarity is usually marked with red and black. Red wires means that's the direction that current can go into the device. Black wires mean that's the direction that current can come out of the device. But on batteries, the plus sign tells you where current can come out of the device and into something else. And the minus sign is where current can go into the battery. Things you're going to need are soft pencil lead, it's a 7B or 8B pencil, index cards or paper or cardboard, anything you can write on, a 9-volt battery, and basic wires. One thing you need to notice when you're making your graphene wires is that really light lines like on the right aren't going to work. You need to make sure your lines are really dark like the ones on the left. So here's an example I've already started. I have the battery connected to 2 graphene wires. And here, this wire is the plus side. So that's where I want to make sure I line up my red wire on my buzzer to have the current go into. And on this side is going to the minus side. So that's where I want my black wire on my buzzer to go into. So here's how it works. Here's an example I made that's cylindrical, and the buzzer is actually inside, and I have it connected to the graphene wires outside. And here's where I could connect my battery. So this is one way to make a flexible device using your graphene wires.
What were you using to record it?
I was using my tablet,
Okay.
but I think within all the reconverting and it getting corrupted and starting over,
That sounds like a tough
the audio messed up.
As far you, we'll keep going, but I think that won't be usable for other people.
Okay, so my project is graphene. With the document, one of the scenarios I kind of thought would make it interesting was that, you know, your sister, your brother, or your sibling, they broke their buzzing alarm and they're really upset about it, but you know some electronic things, and if you just need a quick refresher, you can make it for them again.
Oh, really?
So that was the scenario that I came up with that I think would work with the challenge. Let's see. One thing about the testing apparatus is really just, you know, when you plug it up, does it work? But I did put in here for test the prototype, I put the order in which you should check if everything's working. So I put that, you should check the polarity and the battery are matched up, then check up that the graphene lines are nice and thick and dark, and then check that everything is touching. So I think that's like kind of the best way to debug things if things aren't working. For like going beyond with this challenge, I thought, my professor suggested they could try color pencils, but obviously those aren't going to work half as well as regular pencils, but you can put those out there just so they can see how it's going to work. So that's something to possibly add to the design. And also just changing shapes without changing the structure they're building onto. So like if they use a box, make it so that the box isn't, doesn't have this big hump on this side. So try to keep it the same structure as it used to be. Some big takeaways that I've had from this is really actually kind of resilience, because I struggled a lot in my research, waiting because this device is broke, that device is broke, so that tested my resilience, and even like just this video, changing that, fixing it up. So it actually strengthened me. I had a lot of fun doing it. Working with kids was a lot of fun. I did it a little bit at COSA. I used to volunteer there, but I used to think children were scary. So my view on that has changed, but I think that just changed because I've matured, and I know myself better, that I can relate to children. So what I have up here is just an example I wanted to show of if you decide to tell them to make a switchable device. And so I have the battery hooked up here, and when I move these paper clips, when it's all hooked up, this could make it switchable. So I just wanted to show that as well.
That's a great addition.
So
It's
that's my
all right. Yes, you may. Elsie, do you want to go next after that?
No.
You're staring me down. All right, Jones next. All right, Josh, you got it then.
so like this is the switch. So this is all.
I guess you can just, just take one so that I can start the video.
Thank you.
So before this video starts, for those of you who are not in this class, my name is Joan Lee. As you guys said, everyone introduced themselves. I was like, probably should have done that. And I'm a sophomore in web engineering.
Great. Thank you, Josh.
Yeah.
Did you know that your teeth is mostly porous? What? Like a sponge? No, that's not right. The porous part of the tooth, which is called the dentin, is the brown straw-like structure which covers the tooth. And the white part is the enamel. Sometimes when you eat cold food like ice cream or hot drinks like the teeth can get really sensitive. Why might you ask? When the dentin tubes are revealed, the nerve ending is exposed, and that causes teeth sensitivity. Scientists have developed a new product called Novomin, which is supposed to treat people with teeth sensitivity. Here's how it works. Novomin comes in the form of toothpaste. While you're brushing your teeth, the bioglass particles mineralize onto your dentin tubules to create a protective layer. So scientists who created Novomin has inspired me to make a fun engineering design challenge for the goal of this design challenge is to design and construct a package using the least amount of material to protect the crayon from melting when it's inside the heated chamber. Alright, first let me explain to you the test setup. You get 2 oatmeal cans and duct them together like this. Try to hair